So we left off with our sort of brief introduction to the periodic table and some brief um, things about some of the elements. But what we're of course more interested in is what happens when elements combine to form molecules. And even with the elements themselves, very few atoms exist naturally as isolated atoms. Most of the noble gases do: helium, neon, argon, etc. Talking about the last column, column 18. But most of the other elements all exist as various molecules. Probably the most important group, and I would recommend remembering these: hydrogen, nitrogen, oxygen, and the halogens all exist as diatomics. So again, hydrogen, nitrogen, oxygen, and then our group 17 elements: fluorine, chlorine, bromine, and iodine. Now you might be wondering, why have I essentially ignored the two elements below iodine? And that's because these are elements that, their natural abundance in the case of acetine is extraordinarily low. It's a very unstable element, and tennessine is a element that's only been made in the lab. So not terribly important at this point in terms of their chemistry. But we do have these 7 that exist as diatomics, and many other elements are actually significantly more complicated than these. Now, what we've drawn here or written here are examples of what we would call a molecular formula. A molecular formula gives the number of each element in a given compound. So for example, the first one we have here, H2, tells us that that compound is made up of 2 hydrogens. And these can be very simple, as we see above. They can start to get more complicated. Molecular formula for water, H2O, says we have a compound with 2 hydrogens and 1 oxygen. H2O2, hydrogen peroxide, 2 hydrogens, 2 oxygens. C3H8, this is propane, which you may be familiar with as a fuel, 3 carbons and 8 hydrogens. Sometimes we might see a group inside parentheses within our formula. So this compound, for example, has 1 aluminum, but the second part, the NO3, is in parentheses. So that means we have 3 of this entire group. So 3 nitrogen. And then because there's 3 oxygen inside the parentheses and we have 3 of this group, we'd have a total of 9 oxygens. Now, we have 2 main types of compounds that we're going to discuss in this course: ionic and covalent. Covalent we'll talk about later on in this course, but right now we're going to focus primarily on ionic compounds. Ionic compounds are made up of a pair of ions. The cation, which we said previously is our positive ion, and an anion, which is the negative ion. Now, in many cases, we can predict what the compound is going to be just by knowing what elements are involved. And that's because the periodic table allows us to relatively easily predict at least some of our elements. So let's bring that back up. And we're going to focus on our main group elements. So for the moment, we are going to ignore the transition metals. They're definitely a bit more complicated in what we're about to do. But what we find is that in terms of being able to predict charges, our first group, column 1, the alkali metals, generally give us a charge of +1. Again, hydrogen is a little bit funny in that it can actually, we see it as +1 in some cases, but it actually can also be -1. So we're going to just ignore hydrogen at the moment. In fact, it's probably more accurate to say that hydrogen is usually not involved in ionic compounds the way that the rest of group 1 is. Group 2, beryllium down through barium, those metals, and again, these are all metals, generally give us a +2 charge. We're now going to jump across to the other side of the transition metals, where we get to group 13. Group 13, when in an ionic compound, will give us a +3 charge. And the reason I say when in an ionic compound, aluminum, gallium, indium, thallium, the metals here will do that. Boron, is in the semi-metals or metalloid category. And boron is not involved as often in ionic compounds. Most boron compounds are covalent, and so that charge doesn't really apply to boron to the extent it applies to these other metals. Group 14 here can go actually either way, plus or -4. And then as we get more into the nonmetals, this is where we see negative charges, so -3, -2, -1. So in general, cations are almost always metals, and anions are nonmetals. So it would be helpful, because it's hard for me to keep multiple things on the screen at the same time, if you have a periodic table in front of you as we work through the next part of this lecture, because what we're going to look at is how we actually form ionic compounds and how we can predict what those formulas will be based solely on the knowledge of knowing what the elements are. So we're going to start out relatively simple. Let's say we had sodium and chlorine. Now you may already know that these combine to form sodium chloride or table salt, but if we didn't know that, how could we have determined that? Well, if you have your periodic table in front of you, we find that sodium in the first column belongs to group 1. Chlorine, being what we call a halogen, halogens are that set of elements in the column starting with fluorine, is in group 17. We said previously that group 1 elements generally get a charge of +1. Group 17 elements, a charge of -1. And so if we want the compound to be neutral overall, the easiest way to achieve that is with 1 sodium, which is again +1, and 1 chlorine, which is -1, giving us a total charge of 0. We could do the same thing with calcium and fluorine. Calcium we find in group 2, which means its charge is going to be +2. Fluorine is in the same group as chlorine, group 17, which means it'll have the same charge, -1. So now it's not 1-to-1. If we had 1 calcium and 1 fluorine, our total charge would not be neutral, but would be +1. In order to offset that, we're going to need to multiply that -1 by 2, and we can do that by having 2 fluorines. So our compound here, CaF2. What about potassium and nitrogen? Potassium, group 1, charge of +1. Nitrogen in group 15. That means in an ionic compound, it's going to have a charge of -3. So in order to make this neutral, we would need to bring the potassium up to +3. We can do that by having 3 of them, so K3N. And we'll do one more example here. Say we had aluminum and oxygen. Aluminum, right below boron, has a charge of +3. Oxygen has a charge of -2. So one way to think about this, if this charge is 2, then we need 2 aluminums. This charge is 3. We need 3 oxygens. Or, we could also think about it as what is the least common multiple of these numbers. That would be 6. In order to get to +6, we need 2 aluminums. And to balance that with oxygen, we need 3 oxygens to reach -6. Now, this is how we find the molecular formulas, but it's not always convenient to have to read off a formula like that. So we need to be able to name these compounds. And naming for ionic compounds like this is relatively straightforward. We name the cation as is, and then for the anion, we change the ending to IDE. So we're going to go back and just pull out the examples we just did, and we'll come up with their names. So NaCl, CaF2, K3N, and Al2O3. So in each case, we're just going to start with the name of the cation or the name of the metal. And so all we've done is we've written out the name of the cation: sodium, calcium, potassium, and aluminum. For the anion, we're going to take the name of the element and change the ending to IDE. So in the first one, we have chlorine. So chlorine becomes chloride. Fluorine becomes fluoride. Nitrogen becomes nitride. And oxygen becomes oxide. Now, how about the numbers? Do we need to indicate those in the name? The answer, it turns out, is no. For ionic compounds, because we can figure out the charge based on where the element is on the periodic table, we don't need the numbers because we already can get it from the information that we have.